Next to integration by substitution, integration by parts is perhaps the most useful tool for algebraically evaluating indefinite and definite integrals. It's based upon the product rule. So just as a refresher for the product rule, if we have two functions u of x and v of x, the derivative of their product is of u times v would be u prime of x, v of x plus u of x, v prime of x. Now let's anti-differentiate or compute the indefinite integral of each side. If we integrate, or if we take the antiderivative of the derivative of u times v, the prime simply goes away. Again, the antiderivative of the derivative is the original function. So if we integrate each side, the left side becomes just u of x times v of x, and then we'd have the integral, the indefinite integral of this, and the indefinite integral of that. Now what we'll do with this formula is we will solve for this integral right here. So we will subtract this from the left side, and we're going to switch the order, so this is what we have. So the integral of u of x times v prime equals u of x v of x times the integral of u prime times v. This is the integration by parts formula. Notice how inside this integral the prime has switched from v over to u to give us this new integral formula. So the integration by parts formula is given by this. We use integration by parts when we have a product of two functions, one of which is easy to differentiate, that's u, and one of which is easy to anti-differentiate, and that's v. And if we can do that, if we can easily differentiate u and anti-differentiate v, we can use this formula, and what's important is that the prime switches over to u. So let's take a look at an example, x times the natural log of x. Now this is not on the list of known antiderivatives. This is not something we could actually do by substitution. Had this been the natural log of x times 1 over x, or the natural log of x divided by x, we could use substitution with u equals the natural log of x. Now we have a product of two functions. We know how to differentiate x. We know how to anti-differentiate it as well. But the natural log of x is a function that we know how to differentiate but not integrate. Let me say that again. The natural log of x is a function we know how to compute the derivative of, but not the antiderivative. So this is suggestive of letting u be the natural log of x because we know how to compute its derivative, and letting v prime equal x, whose antiderivative we can easily compute. So typically what we do is, once we make an educated guess as to what u and v are, we write down u and v prime, So u is the natural log of x, its derivative is 1 over x. V prime will be x, and the antiderivative of that by the power rule is x squared over 2. Now let's use the integration by parts formula. The integration by parts formula says that this original integral is u times v. So here I have my u times my v, and then we have to subtract the integral of v times u prime. So in the integration by parts process, there will always be a second integral that we have to evaluate and a minus sign right here. So here is my u prime, and here is my v. Now, for that second integral, let's see if we can simplify it. This is just x over 2, or 1/2 x, and we can easily anti-differentiate that. So our final answer would be the natural log of x times x squared over 2 minus 1/2 times x squared over 2. That's the antiderivative of 1/2 x. So of course we could simplify this to be x squared over 4. So again, we identify our u, we identify our v prime by looking at the integral. We need to compute u prime, we need to compute v, and then we use the integration by parts formula, and there will always be a second integral to evaluate. Here's another example. The natural log of x dx. Now we don't have a product of two functions on the surface, but we do if we simply add times 1 here, because now we're in a similar situation as to what we had before. We know how to differentiate the natural log. We know how to anti-differentiate 1. So u would be the natural log of x, whose derivative is 1 over x. V prime would be 1, whose antiderivative is just x. And I should point out that we don't need to worry about the constants here. The constants will all come out in the very end. So the integration by parts formula says that once I've figured out u and v, I'll have u times v minus the integral of u prime times v. 1 over x times x is just 1. So I'll have the integral of 1, which is just x, and this minus sign comes from that, and then plus c because this is an indefinite integral. So if the function inside is simply one function whose derivative we know, but whose antiderivative we don't know, that's typically a tip-off to use integration by parts where v prime is 1. Here's another example. The arctangent of x. We know how to compute the derivative of the arctangent, but not its antiderivative. So we could let u be the arctangent of x and v prime be 1. We won't actually compute this here, but that would be how to do it. Let's look at a definite integral, dealing with the endpoints. Okay, so I have the integral of x times the sine of x. X times the sine of x. I have a product of two functions. I know how to actually anti-differentiate x and differentiate it both ways with relative ease. The same is true with the sine of x. Now I'm going to choose u in a particular way, and then I'm going to show what happens when we reverse the choice. So let's let u be x, whose derivative is 1. V prime will be the sine of x, whose antiderivative is minus the cosine, antiderivative. Then the integration by parts formula says that I have u times v, so that will be x times minus cosine of x. And now, because this is a definite integral, I have to evaluate this at the endpoints. And then the other part of the integration by parts formula says that I subtract the integral of u prime times v. And now I add back my endpoints, 0 to pi over 2. So I have to substitute my endpoints into this. I'll have pi over 2 times minus the cosine of pi over 2. And then I have to subtract 0 times minus the cosine of 0, which I won't even write down because I'm going to have a 0 here. Then I have to subtract this integral. Now there's a minus sign here and there's a minus sign, and those will cancel. So I'll have the integral from 0 to pi over 2. This is very common when we're dealing with trig functions that will have a plethora of negative signs and there might be some cancellation. Now the cosine of pi over 2 is 0. So that means the first term arising from this will go away. So this will all simplify to be 0. And then I'll have the integral from 0 to pi over 2, which is merely the antiderivative of cosine evaluated at 0 and pi over 2. So that will be the sine of pi over 2 minus the sine of 0, which is not pi over 2. It's actually equal to 1. In general, if you have something like x times the sine of x, or x times the cosine of x, or x times e to the x, integration by parts is your go-to approach with u equals x. Now what if we had instead chosen u to be the sine of x and v prime equals x. You'll observe in this example that we know how to anti-differentiate both x, and we know how to differentiate and anti-differentiate the sine of x. What happens if we would reverse the choice? So in other words, going back to this, forget about the endpoints for a moment. What if we tried to let u be the sine of x and v prime be x? Now if u is the sine of x, u prime would be cosine of x. V would be the antiderivative of x, which is x squared over 2. So the integration by parts formula says that I would have u times v minus the integral of u prime times v. U prime, which is right here, times v. Okay? Now, when you use the integration by parts formula, you'll have a starting integral, and that's going to give rise to a second integral. You want that second integral to be easier than what you started with. And what we have here is we have something that's actually harder, because now we have x squared over 2 times the cosine of x. So we actually haven't made our original integral into something smaller. We've actually made it harder. And that explains why for the preceding example it was better to let u be x and v prime be the sine of x. Here are some problems for you to do in preparation for class. The integral of x e to the x. This is an indefinite integral. And then the integral from 0 to pi of x times the cosine of x. And this should be given as an exact value.